a very, very short introduction to Bluespec. A lot of the explanations I'll be using here is kind of non-generic. I'm focusing on the popular use cases and sometimes not talking about how the corner cases and things like that, which we don't really need for the lecture. So hopefully this will be the simplest introduction that we can get into. So if you're familiar with languages like Verilog, all of these nomenclature is probably very familiar. Bluespec code is organized, everything is organized into modules, kind of like Verilog, where everything is organized into modules. And every module has an interface which other modules use to access state, internal state, kind of like class methods, pretty much, interface class methods. A Bluespec model, whatever that you build in Bluespec, consists of a single top-level module consisting of other modules, et cetera, et cetera. So this graphic here is a little bit wrong because there should be another top-level module encompassing all of these two modules. But yeah. And modules consist of pretty much RTL stuff. It consists of state, expressed in terms of other modules and whatnot, and behavior expressed in terms of sequential circuit expressions. State could include things like registers, FIFOs, memory, and behaviors are expressed with things like rules, functions, and interfaces, and we'll get into that in a bit. And since we're talking about modules and interfaces, if you peek into a RISC-V processor developed in Bluespec, the processor module, in which all the processor stuff, including the PC you see on the left here, the register file you see on the left here, and sequential combinational circuits for the pipeline stages and whatnot, they'll be encapsulated into this make processor module, MK processor, which exposes the interface processor IFC, which is shown here. And at the top level code can actually instantiate a processor as we defined it using the syntax as such. You won't have to understand the syntax right now because I'll get into it very quickly. And to do the fastest hands-on introduction to the language syntax and semantics, there's a simple example that I wanted to use. The Euclid's algorithm for computing the greatest common divisor, in which you start with two numbers, x and y, and you want to discover what the GCD for these two numbers is. Let's say x is 15 and y is 6, and we want to discover the GCD for these two, between these two numbers. And this algorithm follows two conditions. If x is larger than y is subtracted from x. If x is not larger than y, if x is larger than or equal than y, the details are not important for correctness. If x is equal or larger than y is subtracted from x. If not, the two numbers are swapped. So we start with 15 and 6. 15 is larger than or equal to 6, so we subtract 6 from 15, giving us 9 and 6. 9 is still larger than 6, so we subtract 6 from 9, giving us 3 and 6. Now 6 is larger than 3, so we swap, giving us 6 and 3. 6 is larger than 3, so we subtract 3 from 6, giving us 3 and 3. 3 is still larger than or equal to 3, so we subtract 3 and 3, which turns x into 0, at which point y is the current value of y, which is 3, is the answer. The greatest common divisor of 15 and 6 has been discovered to be 3. So we just follow these two rules, either subtract or swap repeatedly to get the answer. And here's the Bluespec code, which implements this. We'll look at this piece by piece. If we look at the, so this module consists of 3 different things, classes of things: state, definitions of state, definitions of behavior, and the interface. If you look at the state, we see these are fairly straightforward things. We define two registers and a FIFO. The actual syntax of the definition may be a little bit more involved, but for our purposes, it's enough to say what this is doing is it's instantiating a register of type 32 bits, and it's being initialized to 0. That's pretty much all we need to know for now. For FIFOs, it's similar. It's a FIFO F. There's a slight difference between FIFO and FIFO F, but I'll get into that in a bit. It's a FIFO of type bit 32 called outQ, which is a FIFO of size 2. It's since all the hardware FIFOs are of static size, it's a FIFO of size 2. So in this module, we have two registers and a FIFO. And what do we do with these two registers and a FIFO is operate on them using rules. We wrote two rules to express the two rules of the algorithm. The first rule is to swap data if the value of x is larger than y. I guess this doesn't exactly one-to-one match the algorithm as expressed earlier, but for the purpose of describing the syntax, this is fine. So if x is larger than y, we swap. And swapping is done in, if you're familiar with Verilog, this might be natural to you, but I'll get into this. For software developers, it might feel a little bit strange, because if you do x equals y and then y equals x, at the end of this execution, it feels like x and y should both have values for y, but this code actually does swap. And if the rule, for the second rule, if x is smaller than or equal to y, and of course, if y is not 0, then y equals y subtracted by x. And if, again, instead of checking if y is 0, we're checking whether y minus x is 0. We'll get into y in a bit. If algorithm is supposed to finish, then we're inserting the answer to the output FIFO. And once the answer is in the output FIFO, these conditions on the top next to the rule names are called guards. And these rules only fire, each rule only fires when the guard is true. That's how we express logic algorithms. Similarly, the outside module, the top level module or whatever, can interface with an instance of this module by calling either result or start methods. If the answer is in the output queue, then someone calling the result method will get the results of the first element in the output queue in order, so that's how you get the answer out. And if you want to start this algorithm, you can call start and give it two numbers, a and b, which will be stored each into x and y. And methods can also have conditions. It says if this method can only be called if y equals 0. That's when computation is not ongoing. Right. And interface methods are also atomic transactions. I'll get into what exactly that is in a bit. If the guards are not satisfied, meaning if y does not equal to 0, since methods can only be called by other rules, the rules that tries to call start cannot fire if this guard is not satisfied. So that's how we ensure correctness in our algorithms without having to write too much code checking whether explicitly checking if y is 0 and things like that. Yeah, we don't need to know too much about interfaces and modules at this point because I don't think you will have to write any new modules for at least lab 2 and onwards. But just for sake of completeness, if we want to talk about Bluespec modules and interfaces, modules encapsulate state and behavior, kind of like Verilog modules, with ports and things like that. Or think of C and Java, C++ and Java classes. Like I briefly mentioned earlier, it can be interacted from the outside world using its interface, which has interface definitions, separate from the module instantiation definition. And since many module definitions can share the same interface, you can have potentially build different implementations of whatever things you want to build, different implementations of modules, sharing the same interface. Interfaces can be parameterized like templates, but it's not important right now. So we're going to move on. And interface methods. Methods for the modules, for the interfaces, there are three types: action, value, and action value. This is just for reference more than anything. Action value takes input, it modifies states, but does not return anything. Value methods returns something, returns a value, but cannot modify state. If you write a value method in which you write code to modify state, the compiler will complain. And also you can write an action value method, which also returns a value and also modifies state. Methods, like I mentioned, can also have guards, like the ones you see here, y = 0. Does not allow the execution of this module unless the guard is true. And modules can be, methods can be called in a familiar syntax. If you have module A, which has an action method, you can call it like this, module A.action method. If it has a value method, you can call it like this, using an equal sign. But if you have an action value method, instead of using an equal sign, you use this strange single arrow notation for getting the return value. There's a big reason for this, but for our purposes, it's not important. It's just enough to remember that if you use an action value method, you need to use that arrow notation, or otherwise compiler will complain with a cryptic error message. And there are two types of guards, both for interface methods and both for rules as well. Can either have an explicit guard expressed in terms of if statements, or it can have an implicit guard. For example, the result method, as you have seen, dequeues from the output queue and then returns the value. But what will happen if the queue is empty? Do we need to implement special handlings for this? And that's one of the things that guards help with. So output queue.dequeue is also an action method of the FIFO interface. And this action method internally has a guard for whether the queue is empty or not, because if it's empty, you cannot dequeue. And this introduces what is called an implicit guard, even if we don't express explicitly as an if statement, we want this rule to have a guard when the output queue is not empty. Just by having output queue.dequeue, if the output queue is empty, the rule that calls .result will not fire if output queue internally, if the internal output queue is empty. And this ordering might also feel strange because output queue.dequeue, what happens if you dequeue from something, shouldn't output queue.first return something strange? But this is how it's used. I'll get into why in a bit. If you're familiar with Verilog, this might already be, you might already know the reason. Right. And we talked about state. If you talk about combinational logic, Bluespec, in Bluespec, combinational logic is represented in terms of what is called rules, as we've already seen. If you're familiar with Verilog or VHDL, rules are very, very similar to the always blocks and the process blocks of Verilog and VHDL. And rules can call other methods of other modules. For example, we've already called output queue.enqueue, for example. And of course, this calling output queue.enqueue will also introduce an implicit guard if outqueue is full. For example, you see the code here. A rule, this step 2 rule represents a combinational circuit, like the one you see on the right. It will take input from X and Y, which is state, and then do some computation, and then either write the data back to Y. Well, not either. It writes the data back to Y. That's why it's a sequential circuit in the end, and also calls the output queue.enqueue. It may call output queue.enqueue. And .enqueue also encapsulates more combinational logic. So there's more combinational logic outside of just this rule definition. Well, internally to this rule definition. So yes, but the code itself, syntax feel pretty familiar to all the other languages that you've ever used, except for that ordering issue. So, right. To continue on combinational circuits, uh, uh, you can also use what is called functions. Functions are combinational representations of combinational circuits. It does not allow state changes. So it's pretty much you push in some data, you get some other data out. And functions can be defined within or outside module scope, but typically we use functions outside of module scope just for simplicity's sake. It does not allow state change. So you can define functions like what you see on the left here. It's a function which takes two 32-bit integers, one 32-bit integer value, and returns a 32-bit integer, returns this particular computation, and this function can be called from inside a rule. And if we were to talk about our processor implementation, a combinational implementation of the ALU is implemented as a function called exec. You will see this when you actually look at the code. And pretty much the only strange thing that we've been seeing from this code compared to software languages are the ordering issues, because Bluespec rules are atomic transactions, and which is very similar to how always blocks and Verilog act as well. Every single state term, for example, X and Y and all these things, the rule only has access to the state values from before the rules began firing. So the value written to these things from the previous cycle is the value that these terms like X and Y represent. And state update happens only once at the end of the result of rule firing, which is pretty natural if you think of this as a combinational circuit. Within this current clock cycle, we will do a bunch of things, and then at the end, we will write some value. At the end of the clock cycle, we will write some value to a register or something. If you imagine it that way, you can see why this swap method works. If X equals 0 and X equals Y at the beginning of this rule firing, if we do X equals Y and then Y equals X, the assignment of Y, the value of Y to X, which is writing 1 to X, will only take effect after this rule execution finishes. So X having now a value of 1 will not be visible to this other statement, writing the value of X to Y. So throughout the course of this rule execution, X will always hold the value of 0, Y will always hold the value of 1, regardless of what you wrote to it. So that's how swap works correctly in this manner. And as an aside, if you try to write two values to X in two different statements, it creates the compiler will complain with a write conflict error, because it semantically makes no sense. At the end of the cycle, which value will we write to X? So you have to, if you want to have a different if statements, for example, in which you want to write different values to X depending on the if statement, you will have to explicitly handle that. Right, that's how all this stuff works. So this step 2 rule may be writing some new value to Y, but the value of Y will not change until this rule actually finishes executing. So because the value of Y will not be Y minus X when we actually run into this if statement, it will still hold the same value from when the rule began firing. So if you want to check if as the result of this assignment, Y equals Y minus X, as a result of this assignment, if we want to check if this Y will turn into a 0, we have to actually write this if statement in this way. We have to check if Y minus X equals 0. Yeah. And funny thing is, all of this includes implicit guards as well. Outq.inq will only come into play if Y minus X equals 0. That means instead of this step 2 rule firing only when outq is always not full, step 2 can fire when outq is full if Y minus X is not 0. So the compiler does a deep analysis of the rule to create this kind of correct, more efficient implicit guards is the takeaway. Quickly into FIFOs. Top registers are pretty straightforward. It's just you write something, you read something from the previous cycle. FIFOs are similar. FIFOs are FIFOs. They are fixed size queues. They have a parameterized interface with guarded methods, as I talked about. Regular FIFOs has 3 methods: InQ, DQ, and first. InQ is an action method, DQ is an action method, which will block when the FIFO is full or empty, respectively. And first is a value method. It also blocks when it's empty, when there's no valid data. There's another thing called FIFO-F, which adds 2 more methods, not empty and not full, which returns Boolean values. And this is less important, but it is provided as a library, so you need to import it at the top of the file. But it's already in our lab code, all of that is done for you. Right. And I think the last part of the peculiarities of not just this particular language, also other HDLs, well, some of the other HDLs as well, is the distinguishing between state and temporary variables. State is state that is maintained across clock boundaries. Yeah, it's defined outside rules. Data is stored maintained across different clock cycles. And all state updates happen atomically, as I mentioned before. All the data is read at the beginning of the rule execution, and everything is updated once at the end of the rule execution. States that we typically use include things like registers, FIFOs. In the processors, also register files are state elements. And if you want to write something to a register, you use this double arrow notation. And if you use this double arrow notation for a register, the value will be updated at the end of the rule execution. You can also use temporary variables, which are just temporary labels given to values within rules or functions. Data is local to a rule execution. Once your rule execution finishes, that information is gone. And that follows sequential semantics similar to software languages, and we'll get into details in the next slide. And this temporary value assignment uses the equal sign, the familiar equal sign. So here's an example. Let's say we have 2 state registers, 32-bit registers A and B. And inside the rule, we are creating not a register, but just a bit variable. Note the lack of register. We are creating a bit variable, temporary variable C, which holds the value of A plus 1, as denoted by the regular equal sign. Also, there's a 32-bit temporary variable D, which holds C plus B divided by 2, as denoted by the regular equal sign. And because these are temporary variables, which follow regular software like blocking semantics, C equals A plus 1. Now, after this after this line in code, C will hold a value of A plus 1, which is 2. After the second line of the rule, D will now hold a value of C plus B divided by 2, which is 3, which is different from registers. If C and D had been registers, regardless of what we wrote to the register in line 1 or 2, for the remainder of the rule, this change will not take into effect until at the very next cycle. But because these are temporary variables, once we make these changes in line 1 and 2, the changes will be visible to us in the next cycle, visible to us in the remainder of the rule. So if you were to write a D to A, D has been calculated to be 3. And this will result in the state element A having a value of 3 after this cycle, but not during the remainder of this cycle. So if we do B, which is another state element, B equals A plus D, A used to be 1 at the beginning of time, as you can see from the top line. If we are doing B equals assign A plus D to B, A will not be 3 at this line. It will still be 1. And but D will be 3. So state B will be 4 after this cycle. But if we had more lines of code after this last line, in the context of those lines, B will not hold a value of 4. It will still, well, it will, the original value was 4 anyway, so it would be the same. But anyways, assignments happen at the end of rule execution. And this is pretty much the same semantics as other HDLs like Verilog and VHDL. But this is one of the things that trips up people when they first get into HDLs. And this is also why you can have FIFO.DQ before FIFO.first, because FIFO.DQ will not take into effect after a rule execution actually finishes. So even if you have FIFO.DQ before reading FIFO.first, FIFO.first will still read the value in the first slot before the rule execution started. And another interesting caveat of HDLs in general, and also for Bluespec, if you have a bunch of rules that express computation and whatnot, at every cycle, all rules that can fire will fire. So if you have 10,000 rules in your project, and all of them can fire at every single cycle because there's no guards, or all guards are satisfied all the time, and there's no conflict between rules. For example, 2 rules trying to write to the same register will conflict. As long as there's not that, all rules that can fire will always fire. So this is how, if you are to talk about computation acceleration, that's how you define or create fine-grained parallelism. Because if you have 10,000 rules, each doing, let's say, a multiplication operation, you will be doing 10,000 multiplications per cycle. And that would be a big deal. The problem is how do you actually route the data to and from this computation grid. But rules will not fire at a particular cycle if at that cycle a guard is not satisfied, or if there's a conflict between rules. Conflict happens, and there's a couple of fringe cases as well, but in general, conflicts happen when 2 rules are updating the same state. For example, writing to the same register, or in-queuing to the same FIFO, or dequeuing from the same FIFO. Interestingly, the way FIFOs are designed is if you have a FIFO and one rule in-queue into it and the other rule dequeue from it, is fine, they do not conflict. But if 2 rules try to in-queue to it at the same cycle, they will conflict. And when conflicts happens, only one rule fires. And typically, the first one in the source file, as the first one that's defined will fire. The other one won't fire at all. So in the worst case, if you have 2 rules that always conflict, and the first rule always fires, then the second rule will never fire. Okay, so that was a lightning round of Bluespec.